for the people to arrive.
Mm-hmm.
Welcome everybody. So we'll wait a couple of minutes. We're already late, so maybe a minute before beginning this session. Okay, so welcome everybody. I'm Martin Trépanier. I'm professor at Polytechnique in Montreal. So I will be chairing this session this afternoon, session 4B, Analytics for Improving Prediction Accuracy and Other Applications. I have the pleasure to have every presenter here connected. So the first presentation will be by David Duong. I will let him present himself and get his title also. And as a reminder, there's questions that you can ask in the Google Docs. So you have to come back to Union Station webpage, access the Google Docs, and you can ask a question during or after presentation, and use. Don't forget to use in the different section of the document for each presentation. So I will ask David to begin, and thank you all for attending.
Hi, so I'm David, Manager of Transit Data and Technology at the IBI Toronto office. I'm presenting a project that my colleague Farah Machlab and I did for Metrolinx to kind of look at Metrolinx's prediction accuracy and kind of help them automate it. Metrolinx retained IBI to look at the real-time prediction information that they provide to customers to ensure that it's accurate and precise, because they highly value the customer experience that they provide to their ridership. So as part of the project, we proposed a 4-step methodology. So the first one was to map the data flow for GoBus and GoRail, as the data is created at the vehicle, and then it flows to the vehicle tracking system, to the prediction engines, all the way to different customer channels. Second step, we help them create like scripts to analyze the prediction accuracy for the different services. And then the third step, we looked at data integrity, so ensuring that as data was created at the vehicle and then going to the various hops to the various customer channels, that the data integrity was maintained. And 4, kind of set up a framework to identify issues and then identify potential root causes so that Metrolinx could rectify the issues and improve their data accuracy over time. And so this is kind of the first step that we did. We mapped the data flow for GoBus and GoRail. So I'll talk about GoRail. So for GoRail, the vehicle creates GPS information and it feeds into internal vehicle tracking system called Trip Manager, which feeds into internal databases, and then goes to various customer channels like station signage, and also via open API to their mobile app and also to their website. So for this project, Metrolinx only provides departure information to their customers. So our prediction error equation was the actual departure time minus the predicted departure time. As you can see, for bus and rail, we had different thresholds because the modes had different characteristics. And then if you look at the bottom figure, so as the vehicle gets closer and closer to a stop, closer to the actual departure time, the prediction error thresholds get more stringent, because as you get closer to the departure time, any errors is felt more pronouncedly by the customer. So using the equation that we showed, we looked at the prediction actually for go bus and go rail. Here I'm showing for go rail by day. So the first figure shows kind of day type, like what the prediction accuracy was for weekday, weekend service. And these are 7 days, so from Monday to Sunday. Prediction accuracy for go rail is pretty good for the study data that we used. And then we also did it by route. So here we're showing prediction accuracy by route level. So the 7 different lines for go rail. So at the route level for Kitchener line, GT, and for Milton line, there's some issues in the 3 to 6 minute bin. We also did it by stop level, which we're not showing here. So for every route, we looked at inverter stops. So for go rail, as part of the study, we looked at different trends. So go rail overall had strong prediction accuracy. And then 3 to 6 minute bins had some issues for certain lines. And when we looked at the route / stop level, we identified 32 Primex stops that had issues with their prediction accuracy. And as part of the analysis, we worked with Metrolinx to kind of find root cause. So one of the root causes was kind of the configuration data in your vehicle tracking system. So here for go rail, like the geofence configuration for the stops could have been what caused the problem for these 32 identified. And then construction could have been an issue as well, where if you don't put in construction data into your prediction engine, that could cause issues with the prediction accuracy. So as part of our work for Metrolinx, we kind of provide them an example of a dashboard so that they can automate. We use the scripts that we provide to automate the prediction accuracy reporting, and then recommend that they set up a regular review and issues resolution framework to continuously improve their prediction accuracy over time. Because when you provide poor prediction to your customer, that causes them frustration and can also affect the reputation of your agency. Thank you.
Thank you, David. So, okay, so if you have questions, you go in the Google Docs and put them in, or just ask, try to get some, to get more information. So the next presenter will be Sean O'Groden. He's from Georgia Tech. So Sean, you can share your screen. You ready? Thank you. So, you may initiate the presentation mode.
Okay, can you see my screen?
Yeah, it's working well. Thank you.
Okay, I'll start. Hello, my name is Sean O'Groden. I'm an independent developer from Ireland, and along with Simon Berrebi, I'm a maintainer of the Transit Clock open source project. This presentation is about an open source framework we implemented in the Transit Clock to support the Kalman filter to generate bus arrival predictions. David's covered some of this, but why bus arrival predictions? Well, it increases passenger satisfaction, perceived reliability, and actually improves the wait times for passengers. But even though you provide predictions, it's important that you actually provide accurate predictions, because providing inaccurate predictions also has a negative impact. And again, just the current situation with the virus, it's kind of important to provide accurate information to passengers given the number of changes. Anyway, the Transit Clock project, which I'm the maintainer of with Simon, is an open source project that provides arrival predictions to a number of cities across the world. Just to give a context, it provides predictions in Minnesota, Florida, Washington, 2 cities in Poland and Europe, and 3 cities in South America. Okay, what we did with this is we implemented a Kalman filter within the transit clock. The transit clock provides a framework for providing the data to support such a filter. So the Kalman filter's inputs, which the transit clock provides, is the travel times for the previous bus on the route on the same day as the bus is traveling. The other input that we use to the Kalman filter is historical data for the X number of days in the past for the same trip is also passed into the Kalman filter. These two sets of data are combined within the Kalman filter to generate a prediction. Now the Kalman filter is very suitable to work like this because it's an iterative algorithm, and it's also an iterative, adaptive, and recursive algorithm. So it balances its the weighting between the times for the last bus against the historical times based on the error from the last prediction. So in this case, it's adaptive, and it's based on a paper from Shalaby and Farah that was published in 2004. And this algorithm that we placed inside the transit clock got a good outing, and was its performance was measured as part of an innovative procurement process that was started or set up by Metro Transit in Minneapolis. So what they wanted to, they asked several vendors to compete, running predictions for 1 month on, well, they have 1,400 vehicles, so you get a size of the agency, and they've in the region of 250,000 passengers per day. And they did a comparison between 3 different systems: a competing proprietary software system, the legacy system which they have running within Metro Transit, and the transit clock which we put forward with it configured to support the Kalman filter as described. And the next 2 slides is just we did our own analysis of the prediction accuracy, but also Metro Transit did an independent analysis because it was a tender process. So I'll just describe the results that we've seen. This is our graph, and what we're looking at on the x-axis is the horizon. And as you can see, that the further the bus is away from arriving at the actual stop that it's predicting, the larger the error. This is what you would expect. So if you're 20 minutes away from a stop, you would expect the prediction not to be as accurate as if you're 5 minutes away from the stop. But as you can see here, the transit clock error for both the 75th and the 90th percentile is wholly enclosed within the prediction error of the legacy system that's been run in Metro Transit. So therefore, at all horizons, the Kalman filter method for predicting travel times outperformed the legacy system. Now that's our measurement of the data. Now the independent measurement of the data by Metro Transit was done in a different manner, but similar to what David spoke about. The orange line here on this graph is the performance or the percentage accuracy of each of the different methods. The orange line being the transit clock, the blue line being the competing proprietary software, which is based on the historical average, and the legacy system that was in Metro Transit. Now, in this graph, you can see that the prediction accuracy improved for the whole month of the pilot based on for the transit clock. So it is an adaptive algorithm. But I'd like to highlight in particular the 24th of October, where there was a demonstration, a protest in relation to a football match that was happening in Minneapolis on that day. So there was significant disruption within the city. So you can see from this graph that the legacy system and the competing software prediction accuracy on that day dropped off to a significant extent, but the transit clock's prediction accuracy remained above 80% based on a measurement by an independent measurement by Metro Transit. And the graph there, it was generated by Eric Lynn from Metro Transit. Just in conclusion, the Kalman filter, as I said, is an adaptive algorithm. In this case, we implemented it at scale and it has been selected to provide the predictions in Minneapolis for the next 4 years. It performs better than a historical average and is certainly more robust under disruption. And we plan to improve on this work by considering dwell times in a similar manner and also looking at disruptions and detours. Of course, I'd like to thank the people that were involved in the pilot in Metro Transit, that being Laura, Eric, Joey, and Ben, and of course our partners, Cambridge Systematics and Raphael from there. If you want any more information on this implementation, you can contact us on info@transitclock or look at our website, transitclock.org. Thank you.
Thank you, Sean. Right on time. So I remind if you have questions, you put them on in the Google document. So the next speaker will be Ricardo Giesen. So Ricardo, whenever you're ready.
Sure. I hope you are seeing my screen right now.
Yeah, it works well.
Perfect. So I'm going to talk about machine learning approach to estimate transit travel time using sparse data on GPS. This was the master thesis from Ramón Bahamonde, who I co-supervised with my colleague Hans Löbel at the Department of Transport and Logistics at Catholic University. So here the main goal was to estimate travel time for buses in scenarios with scarce data. So you have a low frequency running bus, and we were looking at the beginning using data from parallel corridors and applying learning methods. We can do a good estimation of the travel times. So we did a case study with data from Santiago. We have data on the buses running in the city. And our experiment, and I think I can show here, was on this corridor, which is Avenida Pedro de Valdivia. It's a main corridor north-south in the city. And we were taking data also on Manuel Montt Avenue and Los Leones Avenue, which are parallel corridors. And we are going to refer to this as the segment of interest and the parallel segment A and parallel segment B for the time being in this presentation. So I'm showing you here pictures of the different corridors. Here I have some data about the corridors. I'm going to concentrate on the segment of interest for these 4 different periods. And you can see that even though there are corridors that are parallel on the city, they don't have exactly the same travel times. So roughly parallel segment B in the morning peak is very similar in terms of travel time to the segment of interest, but the parallel segment A is much faster. Then both are faster on midday. In the evening peak, this is slower, this is faster, and you can see that there are differences. But using this as a way of getting data on parallel segments, we wanted to try how much can we improve on the way we do the predictions for our corridor. So we compared 4 different models. So we used linear regression, support vector regression, and feed-forward neural networks or neural networks for simple. And we compared these 2 against historical average data. So that's what you would do if you have the historical data and you take the average for a certain period and certain segment. And last period average is to use the real-time information and to take the average on the last period. We took some aggregated variables to do our comparisons for the segment of interest, and for the 2 parallel segments, we use travel time from historical data and from real-time data, and we use also standard deviation from historical data and from real-time data, and all for the segment of interest and the parallel segments. And we use the dummy variables to indicate in which period are we doing the computations. And then we computed 4 case studies. Here is my a graph of that try to represent the case studies. So here I have different time slots of weeks of data, and I have historical the data on the previous period and the period in which I want to do the prediction, and only I can have the period t+1 for historical data. I don't have it for the current time that I'm doing my predictions. So the first scenario was using only current time slot data. So that would be to use only the data that is here for the same segment of interest and data for the parallel corridors during this scenario. For the second case study, we use current time slots for parallel segments. This is the case in which we don't have information for the segment of interest, and we want to do an estimation of the travel times on the segment of interest based on the information on the parallel segments. Then we go to a scenario in which we only use historical data for all segments, and we the last one in which we use all the information available. So I'm going to show you the results right away. So first we studied the effect of GPS data sparsity, and we go to take only 50% of the data available, 30% or 10%. We quickly identified, and we did all the typical things to do this comparison. We do 70% of the data to calibrate model, 30% to validate and to estimate the mean square error that I'm showing you here. And we do it fivefold cross-validation to estimate the parameters on each one. So as we see the historical average and last period average, do a decent job when you have a lot of data, but as the data start to be scarcer, you get to a higher level of inaccuracy in your estimation, whereas on the top models, you get to see that these improvements are not, you keep maintaining good estimates in all these scenarios. Then we study what would be the impact of having additional information on historical data and using the parallel segments. And you see that for vector regression and for linear regression, adding information on the parallel segment can improve the quality of results. And we didn't get very good results with neural networks. So I'm going to jump into the conclusion so that I have enough time. So we test on real bus data for Santiago. We showed that information on parallel segment can generate improvement if paired with robust prediction models such as support vector regression. In all time intervals during the day, the use of non-local information provides an improvement in performance, particularly in scenarios with sparse data and with high variance, such as evening peak or night intervals. In case without data from the segment of interest, we were able to obtain similar levels of error to those obtained when using the segment of interest data, and that is very interesting results. Among the models evaluated, neural networks showed poor results due to the overfitting, and linear regression and support vector regression models produced similar results when using local information. But the addition of parallel street data produces a clear advantage to support vector regression. Overall, and summarizing everything, we recommend the use of support vector regression for applications in which data for street is sparse, or it will be complemented with data from parallel avenues.
Okay, thank you. So there will be more details in the longest presentation. Thank you, Ricardo. So okay. We go to the next speaker. The next speaker is Ryan Williams from Toronto. You can go ahead and share your screen.
Great. Yep, I'll just share my screen. Okay, so I'm going to be talking about a proposal for a framework for real-time bus travel time prediction with reliability sensitivity. This is something we've been working on through the Transit Analytics Lab at the University of Toronto. I'm just going to hop right into it since I do not have a lot of time. So there exists a body of literature on transit travel time prediction, in which models have been tailored to different aspects of the transit operation. The framework proposed here is meant to deal with the transit context in which the level of operational reliability varies significantly. Now, reliability, of course, can be measured in a number of ways, and this is one of many considerations when prototyping a reliability-sensitive prediction framework. The proposed framework consists of three major conceptual pieces: reliability sensitivity, which I'll explain in more detail in a minute, machine learning, which provides us with advanced models for predicting travel times, and sequential prediction, which describes our choice to predict travel times on a segment-by-segment basis rather than produce single predictions for multi-segment stretches of a transit route. So a service might be considered unreliable if it is operating on a busy corridor with a lot of riders and is subject to delays that cause arrivals at stops to differ from the schedule. Real-time data streams that provide information about a vehicle's whereabouts can be used to inform predictions of downstream arrivals, but the data themselves are sometimes unreliable as well due to reporting errors or system malfunctions. By measuring service reliability and separately measuring data reliability, we can construct a two-dimensional reliability space, shown here, that can be separated into regions of different behaviors. So we've got an axis for service reliability and an axis for data reliability. Within each region, the task of predicting travel times may require a different approach or be suited to a particular prediction method. And what we're hypothesizing here is that if we assemble a catalog of prediction models tailored to each region of the space, and then call upon these models in real time based on the most up-to-date assessment of the two types of reliability, that we can achieve better prediction performance than if we had a single model for all conditions. This graphic outlines the framework as it would operate in real time. When a vehicle leaves a stop, real-time information is used to measure the reliability of the service, as well as the reliability of the data stream. And this joint assessment places the prediction context into one of the regions shown on the previous slide. The appropriate model from a catalog of models trained using historical data is selected and used to predict the travel time on the upcoming segment. The travel time to the next stop informs a predicted departure from that stop, and that departure time is then used as an input for a subsequent segment prediction. Linking segment-level predictions together to give downstream travel times ensures that predicted stop arrivals are internally consistent and potentially allows for the reassessment of reliability conditions based on predicted movements from one stop to the next. Once travel time to all stops up to the end of the route have been predicted, the system waits until the next stop departure and then updates those predictions. So here we see a sample trip from a case study that we did on a bus route in Toronto. So Route 36B, Finch West, runs for about 6.3 kilometers between two subway stations and experiences issues like inconsistent running times, bunching, and delays resulting from operating in mixed traffic. The real-time system used to collect this data has its own reliability issues. So you can see here, for example, that on the black line, one of the segment travel times is reported to be 0 seconds, and a few others are unrealistically short or unrealistically long. The gray and blue lines show predicted trajectories beginning from actual departures at various distances downstream. As one would expect, the prediction accuracy at the end appears to improve as the number of segments between the last reported location and the terminal decreases. Assembling the catalog of models for this case study involved testing a variety of explanatory variable combinations and choosing the best of several different regression models that included ordinary least squares, decision tree regression, k-nearest neighbors, support vector regression, extreme gradient boosting, and artificial neural network regression, as well as a simple moving average. So we can see on this graph, which shows absolute prediction error for different configurations of the framework versus the number of segments downstream, that errors for segment predictions are compounded over longer distances, as we would expect. The black line describes the downstream accuracy of the sequential prediction framework with a two-dimensional reliability space, as discussed earlier. We can see that for predictions at long distances, it performs better than when a single model is applied under all reliability conditions, shown in red and referred to here as a global model. The blue line describes the accuracy of a configuration in which there is reliability sensitivity, but where predictions are continuous over multiple segments, rather than broken down by segment as in the sequential prediction. We see that this framework configuration delivers poorer performance for short distances, but is comparable at several points downstream. Now, this graph shows the results of testing improvements to the reliability sensitive sequential framework. The original configuration, again, the black line, only assesses reliability when an actual departure occurs, and the resulting reliability region is assumed to be the same for all segments up to the end of the route. The green line, on the other hand, shows an attempt to improve on this by reassessing service reliability based on the most recent trips to be observed at each downstream stop, making the service reliability assessment more dynamic within a predicted trajectory. Reliability is characterized with a number of different measures, and for each measure, there must be a threshold between the reliable and unreliable sides of the reliability space. Adjusting these thresholds to better reflect distinct conditions can lead to further improvements in accuracy, as shown by the orange line. So just to briefly conclude, it appears that reliability sensitivity can offer an advantage when predicting bus travel times in real time. Testing shows that the proposed framework could perhaps be improved by constructing the reliability space in a way that better reflects distinct conditions. Future improvements to the framework might involve investigating composite measures of reliability that simplify the characterization of incoming data, or to introduce medium reliability regions to the reliability space. And there are a lot of other details about this that I'd be happy to discuss in the Q&A, and that will be available in the long form slides as well. Thank you, that's all.
Thank you. So you already have a question on your Google Sheet, so we'll come back to it afterwards. The next speaker is will be Carlos Olivos. So you can share your screen whenever you're ready.
Very well. Okay. Do you see it?
Yeah. So okay, thank you. Go ahead.
Hello, everyone. Today I'm going to present you the danger zone of express services. This is a work we've done with Professor Homero Larrain and Juan Carlos Munoz at Pontificia Universidad Católica de Chile. Now, let us imagine one direction of a public transport corridor. And in this corridor, we have two types of buses. We have an express bus, which is allowed to skip some of the stops along the way, and an all-stop bus, which is meant to stop at every stop there is. Now, let's imagine that we want to improve the conditions, and we choose to raise the express bus frequency. So instead of having it every, say, 15 minutes, we have it every 10 minutes. This should improve the level of service, right? But actually doing so may decrease it even by a lot. What's happening here? What's happening is that we have some flexible users. Flexible users can take both kind of buses, meaning they have two strategies. They either can take the first bus that comes to a stop, or they can only take the fastest bus. This strategy makes sense when the frequency of the express bus is low, because if the express bus comes every hour, for example, taking the all-stop bus will make a lot more sense even when it's slower. But when the frequency of the express bus is high, it only makes sense to take this bus. So if we see this in a graph, if we increase the frequency, we also increase the supply. That is obvious. But there's a little problem here, is that when we reach a certain point we call FE hat, the demand gets also raised by a lot, and it could actually be more than the supply, and this problem could persist until we reach a point we call P, which is the point where the demand meets the supply. What's happening here is that by raising the frequency of the express bus, we make the second strategy far better than the first one, making all the flexible users choose the express service. This allocates more demand in the express service than it can handle, and thus we get long queues of flexible users only willing to take the express bus. If we see this in terms of waiting times, we have here the express queue waiting time and the all-stop queue waiting time. As we increase the frequency, we will meet the two parameters we mentioned before, FE hat and PE. So starting from the left and up, we will see that the waiting times start going down until we reach FE hat, where they shoot up, and they persist to stay up until we reach the point where the demand and the supply meet. All this range of frequencies is what we call the danger zone of express services. So in summary, by raising the frequency of the express bus, we're increasing the supply, but we might also be increasing the demand. And if the demand is higher than the supply, we get this problem, we get a danger zone. Up to this point, we have mathematically determined what the danger zone of express services is. And now we'll try and go further, showing cases that our math model cannot show with a simulation. So in the simulation, we have users, and how do these users choose their queues? There's going to be two queues, a queue for the express bus and a queue for the all-stop bus. Well, it's quite simple. They estimate their waiting times, and they consider the travel times, and they choose the fastest option. So plotting the same graph we had before in another graph, we can throw the simulation results over the mathematical results, which are the one that we're seeing now, and we would have this. Now, we see there's a difference between the simulation in red and the theoretical results in blue. What happened here basically is that the mathematical results consider a continuous discharge rate, while the simulation results work with batches, which is more realistic. And we also see that we have matching borders, which is very good. It means that with the simulation, we actually reproduced whatever we determine mathematically. But this border right here is actually unrealistically abrupt. It would mean that every user has basically the same mentality, and they are all choosing the same thing at the same time, which is really unreal. So do all users estimate their waiting times the same way? The answer is no, and thus we added variability with 3 different levels, and we see that the more variability we put in the estimation that users make, we'll see the left border of the danger zone, that red line, straight up red line there, go more to the left. Now, we could also argue that users could use an app to predict the bus arrival times. What would happen then? Well, as the app penetration grows, the danger zone tends to flatten, with a complete flat green line there when the penetration of the app is total. I could actually explain this to you, but it will take a lot of time. So the intuition behind it is that when a user has an app, taking the first bus that comes to a stop, which was this first strategy, does not make sense. Thus, the left border of the danger zone tends to disappear. The more penetration we have, the more it will disappear. In conclusion, Changing the express bus's frequency affects both the supply and the demand, and it's important for planners to consider it. A high variability in uses estimations does not impede the danger zone from happening, it only flattens it. And if waiting times are obtained with an app, the danger zone still exists. Low frequencies are more affected and high frequencies are less affected. And thank you very much. I will be happy to answer questions in the Q&A.
Thank you, Carlos. Very interesting. I think it will suscitate some questions, especially for the BRT, because usually in BRTs you have also buses that goes express and others more local. Okay, thank you. So the next and the last speaker will be Chiawe Wang from Miguel. So if you'd like to start your...
share my screen?
Yeah, very good. Go ahead.
Okay. Okay, good afternoon or evening or morning. In the next 6 minutes, I will share our study, Dynamic Holding Control to Avoid Bus Bunching, Multi-Engine Deep Reinforcement Learning Framework. And I'm Chiawe Wang, and I'm supervised by Professor Li Junsun. And bus bunching refers to a group of 2 or more buses arriving at the same stop at the same time. In this case, some stops may be served by multiple buses, while passengers at other stops have to endure a longer waiting time. It is a long-standing problem in transit system because of the variability in travel time between stops and the variability in passenger demands. In this case, there will be an uneven occupancy among stops, and the efficiency of the transit system can be undermined. In the past studies, many solutions have been implemented to avoid bus bunching. Among them, the holding control is the most practical and adaptive one because it's easier to implement and it frustrates the passengers less. However, these studies mostly derive policy based on a fixed target headway, which is not reasonable because an ideal achievable headway is neither static nor known in advance. In addition, most studies only focus on local control and there may be lack of long-term consideration. So in our study, we want to explore a multi-engine deep reinforcement learning framework to fix the limitation. In reinforcement learning can consider the long-term effect during control, and the multi-engine framework can exploit the global policy more efficiently. In reinforcement learning, an engine tries to maximize its cumulative reward during the interaction with the environment. In our study, we regard the bus as an engine and the transit system as the environment. And specifically, when a bus arrives at a stop, it will observe the state of the transit system, which is formulated as a vector of 4 elements as shown in this. And based on the state observation, the bus will decide a holding period at corresponding stop, which is his action. And then at his next arrival, he will receive a reward to evaluate his last action. And the reward function we define here is this equation. The first part is to use to encourage the bus to equalize its forward headway and backward headway, while the second part is used to avoid overholding. And we adopt and modify a state-of-the-art multi-engine reinforcement learning framework to train the engines. Specifically, the actor which is used to model the policy it is parameterized with a deep neural network, and we also use a deep neural network to approximate the state value of the action made by the actor. In a simulation study, we consider a ring corridor with 12 uniformly distributed stops, and there are 6 buses evenly distributed in every 2 stops, and we consider a passenger arrival dynamic governed by a Poisson distribution, and we implement this study based on a simulator and a learning model. During model comparison, we compare our proposed method with 4 baselines, and there are the bus trajectories under different holding strategies. As you can see, the black dot means the holding happens, and the deeper color means the longer holding time. And the proposed methods can successfully avoid bus bunching with less holding period. Also, we consider the efficiency in extreme case. The first is that what if the arrival pattern is different from the one in training? That is, during the abnormal arrival patterns, the arrival rate is 20% higher or 40% higher than the training phase. The learned policy also work well. And the other extreme case is that what if there is a demand impulse? In this case, there is a 50 passengers pull into station 3 and bus bunching happens, but the policy can also avoid bus bunching in the long term. So in our study, we developed a multi-engine framework to learn a policy that is more efficient because it can avoid bus bunching with lax holding period. And the policy also can help handle extreme case. In the future, we would like to consider more uncertainties in the free operation, for example, the traffic signal, and then we want to incorporate more available information such as the real-time passenger demand, and hopefully we will test the framework in the real-world fleet operation. Okay, thank you and welcome for the questions.
Thank you very much. Thank you to all presenters. I will ask you just to open your camera, activate your camera, your video, and we'll be able to get the discussion. I would ask, I've seen them, there's some question already in the Google Sheet. Maybe we'll start with David. Would like to address one of the questions you've had in the Google Sheet. There's one actually about do you have access to the Google Sheet, David?
No.
Maybe? Oh, okay, sorry. So there's a question about the prediction. Are the prediction intervals to the actual or the planned arrival? So I don't understand the question myself. In the first, when the prediction is made, I guess it's uncertain which window interval it will end up in. So as I expect in these systems, the prediction is updated each time the bus arrives to a stop or a station. Is that the case?
Yeah, that's the case. Yeah, so we use it's not real-time information that we use. It's really we know already what the actual departure is, and then we use the historical data. So when the prediction was made versus the actual.
Okay, but it's not implemented in the real-time system for the information to the user. That's what I didn't know.
Yeah, I would guess. Yeah, so it's not like a real-time prediction. It's more like it's near real-time because you need to know when the actual departure is. Okay, sorry. Okay, good. Okay, so maybe another question for transit clock. Do you have to add some comments to the question you had, Sean, or?
There was just one thing I wanted to correct was that the graph for Metro Transit was prepared by Joey Reid, not Eric Lind. Sorry, that's an error on my behalf. Just correcting that. One of the questions in the spreadsheet asked what the input to the algorithm is. I've answered that in the spreadsheet, saying it's the static schedule based in GTFS format, which is the normal input to the transit clock, plus the vehicle position feed in GTFS real-time format with a block assignment within the vehicle position feed.
Okay, so if an authority has a GTFS and a GTFS RT, you are able to use the transit clock.
Just to be specific, they only need GTFS RT vehicle position feed with an assignment. They don't need the trip update feed.
Okay.
The transit clock will generate that piece of the GTFS real-time feed automatically.
Okay, very interesting. Thank you. Maybe just a question for Ricardo. Machine learning. So there are a lot of approaches, and I've used some myself. But the method has to learn from something. So machine learning is learning. So how do you think it could be applicable to other streets or other sectors of the city, will you have to relearn the algorithm, or it could be transfer?
So yeah, our idea was to look at if the information parallel segments can inform what's happening on other segments of the city. And in here we did have the data to check, and then we were comparing if we use, as we were taking out some data to do the analysis, how the different methods compare. And yes, I think the idea to extend it to other parts of the city would be to transfer the knowledge that we got here in terms of the problem is if you don't have ground truth, it's hard to know how good or how bad is your forecast. In our case, we did have the data to validate how they performed. So that was the idea on this paper.
Okay. Yeah, because yeah, you can retake part of the algorithm and it will learn over new situations, because that's always a problem. If you have a brand new situation or a big disruption, it's hard for these algorithms to infer what could happen in the network. Thank you. Ryan, I've seen there's some questions in the Google Sheets. I don't know if you have access.
Yeah, I do.
Okay, would you have any comments or
yeah,
response?
I think it's probably good to start by addressing that first one. So someone asked, how does one measure reliability of data in real time? And that's, I actually think that's one of the areas of sort of the framework that I proposed that probably could benefit from more research. What we do right now really has to do with just identifying behaviors that we would consider kind of outlier behaviors. And so you take an observation of travel time on a segment between two stops, and you say, so the time between departing from the terminal of the route and arriving, or sorry, the time between the departure from the terminal of the route and the departure from the stop at the start of the segment, how long is that period of time? And where does it fall on the distribution of historical times that we would see? And so, you know, like we say, for example, if it varies, or sorry, if that period of time differs from the mean, like from the historical mean by more than like 2 standard deviations, then you would consider that piece of data unreliable. And so we do that for we kind of have 4 different measures that work like that, where we're looking at the cumulative time between the terminal departure and the departure at the beginning of the segment, the time between the terminal departure and the arrival at the end of the segment, also looking at the distribution of the travel time itself, and the operating speed on the segment. So with all 4 of those things, we're kind of trying to capture sort of as many aspects of the behavior as we can, such that if any of those things kind of fall outside of an allowable range, then we consider the data unreliable. And that's sort of based on you know, other types of research where you're removing unreliable data, but because we're trying to actually harness data that we think is unreliable, it's kind of it is a somewhat different task, and so right, what we had to go on was kind of like best practices for removal of data and for cleaning data sets, but obviously like this is sort of different. So so always, basically we're just making rules about what's kind of what is consistent with the past, and therefore what we would consider reliable.
Yeah, because we want, for sure, if there's a big disruption, the user wants the good time, and it's always hard. And if the data is too different, it will be rejected. So it's not easy.
And it's a challenge. It's a challenge to figure out at times, especially when it comes to major disruptions. What is the difference between data that reflects severely unreliable service, right? So are we looking at factual data that reflects very unusual circumstances, or are we looking at data that's actually a reflection of a system error? And I think that ultimately it's not always going to be possible to tell. But I think you know, a real area of investigation for this is kind of just like finding more dependable ways of doing that, and of characterizing unreliable data streams.
Okay, so very quickly, the second questions, could you imagine that to adapt this to estimate the onboard load, or it's not?
I think so. That's not something that we've given a lot of thought to in the framework that we have right now. But ultimately what our framework relies on is having a cache of historical information about whatever it is you're trying to predict, right?
Mm-hmm.
Trying to have as many explanatory variables as possible that you have historical information on, right? So like, because we're using these machine learning models and, a lot of them are very data hungry, a lot of the work is sort of has to do with feature engineering and figuring out how we can use the historical and real-time data to feed these models. And that could apply to something like passenger loads as well.
Okay,
it's
thank you.
Just kind of a different, potentially a different set of explanatory variables, and then certainly a different dependent.
Okay, thanks.
Yeah.
Okay, so the next presentation, the danger zone, I think if there's, I don't know if there's prizes for presentation, but it's been appreciated by the public. So Carlos, the first question is very good. Do you think that it could be used to try to estimate the difference in fares that could maybe slighten the effect of the danger zone? I don't know.
We actually haven't discussed using fares to do so, but we have discussed some methods to try to move some of the users that are taking the express service to take the other bus. And that would definitely be beneficial, but we haven't exactly discussed fares, so I cannot tell you for sure the answer to that. Okay.
And the other question, question number 4, it's possible to define an objective that will minimize the service hours that are needed to serve everybody. So the key is, how do we balance between express and local?
That's a complicated question, actually, because it would depend on the state of service you have now. Like, you can be either too far to the right on the danger zone or too far to the left. And the solutions to get out of the danger zone in both cases are very different. So you could actually try to optimize it, but it really depends on the conditions that you have in your corridors, the difference of times, and a lot of things, actually. So I don't know if we could minimize it straight away, but there's definitely a way to do it, and we're trying to find it. Still in progress.
Okay. Thank you. And I know that in Santiago, you have all the data, the GPS and the smart car data. So it could be interesting to take real data and try to see how people behave, especially from one day to another.
We're getting there.
Yeah, I know that you should be working on that. Thank you. I don't know if there's a question also for bus bunching, because this is another very interesting topic, Chawei. It's actually, I think that the next challenge for most authority is that they have real-time controlled services, systems all over the place, data everywhere. But what is the strategy to adapt? What is the strategy to take when there's a problem on a single bus line, when there's bunching, when there's delays? So this is quite interesting. So would you have any comments to add on this topic, Chawei, or? Oh, you're muted.
Okay, can you hear me?
Yeah.
Yes, I think that the most challenging and interesting part is that how to incorporate more available data nowadays to into the model to train the engines, because the more features you fit into the engines, the more more powerful policy you can explore. So I think that in the future works, the more available data should be incorporated, especially when it is nowadays many data can be obtained through many sensors.
Mm-hmm.
So it's really promising to exploit more data to train the engines.
Okay, I will talk to Lee June about that. I have some data for you.
Thank you.
Okay, so if there's any comments, any other questions, I'm looking at Q&R. There's a question. Yes, there was a question. It's not. I think it's for Carlos. In the Q&R, it's for the work. No, it's the work done. Which one? Who's supervised by Homero?
It's me. Yeah, it's me.
Oh, sorry. Okay, so there's a question. Do you see it in the?
Yeah.
Okay.
So they asked, what is the net effect of the express danger on passengers' travel time? Basically, we have two types of users. So users that take the express bus are having a worse condition than the condition they had without the danger zone, and users that are not taking the express bus are basically having the same conditions they had before. So added, it means there's a problem in general. Basically, the net effect is that we are waiting more time than we should be waiting for everyone in this.
That's interesting. Is it in your long presentation or no? It's not at this level. It's not explained, because I think people would like to have your presentation. I don't know if it's on the website.
We have a longer version. I can submit it, and there's a paper, and yeah, and actually in the spreadsheets we answered where the paper is. So if anyone is interested, you can read that.
Okay, so thank you very much, speaker. Very interesting session, although quite short, but you will have more information on the short and the long presentation that can be found. I would encourage people who did not put their presentation yet on the website. I think it can be done and it will be available to attendants. And I thank you very much. We look forward for the next session at 4:30, the plenary. So we'll invite you to come back at 4:30. And thank you very much for your participation. Thank you.
Thank you, Martin, and thank you, everyone. Bye.
Thank you. Bye-bye.